Hi everyone, I'm Xiaoyang from Rutgers University. Today is my great honor to present our work extending coverage of stationary sensing systems with mobile sensing systems for human mobility modeling. This is a joint work with Peking University and SIAT. Our work is set in the background of human mobility modeling, which is an important topic because it enables many applications and services. For example, for city administrators, they can optimize urban planning according to where the crowd is. For the public, predicting the future mobility helps to prevent possible public safety issues. And individual users could also get benefits from many location-based services. To model human mobility, previous works generally achieve this from two aspects, stationary sensing and mobile sensing, according to the data collection approaches. In stationary sensing, the sensing systems are generally stationary, such as cameras, Wi-Fi access points, and smart car swiping stations. When users are nearby, we can know the locations of users. In mobile sensing, the sensing systems generally move with the user, such as a mobile app and car navigation systems. These systems continue collecting users' locations. We found that we can actually put these two approaches in a coordination where the x-axis is the spatial coverage and y-axis is the population detection rate. So why is it? So let's see a simple example. So for example, there is a stationary sensing system consisting of two cameras A and B. Basically, all the users in the camera's view could be captured, which means it has high population detection rate. However, considering its limited deployment, after leaving the coverage, we cannot capture them anymore. For mobile sensing, such as users installing a navigation app, since it moves with the user, it has a high spatial coverage. However, for a specific mobile app or a navigation system, it generally only covers limited users, which leads to a low population detection rate. So far, I hope I convinced you that two sensing approaches have complementary features. Now we introduce our goal. Can we have an ideal sensing approach with both features? Suppose we have a user U star, which is only captured by the stationary sensing system. Then our goal is to infer mobility of U star after leaving the coverage of the stationary sensing system without any mobile sensing system. To achieve this, our key idea is to utilize user similarity. For example, we have a small number of users, U1, U2, and U3. We have their complete mobility traces provided by a mobile sensing system. We find both U3 and U star are detected by A and B at a closer time. Therefore, we guess U star may have similar mobility as U3 after leaving A and B. However, it's not trivial to measure the similarity. In our work, we design a framework called Mohen to do it. Our goal is to find users with similar mobility in the mobile sensing system. However, the fact is that we can only measure them in the stationary sensing system, since only the stationary sensing system can capture all the individual users. To establish this bridge, we design a mobility sequence encoding model to make the measurable similarity approach to the objective similarity. Then, based on the found similar users, we design a mobility sequence prediction model to infer the next location of users after leaving the coverage of stationary sensing. In this way, we virtually extend the sensing coverage of stationary sensing system. In our evaluation, we are based on two real-world systems in a city-scale testbed, a highway toll collection system as a stationary sensing system, and a vehicle GPS logging system as a mobile sensing system. For example, this figure shows the coverage of our systems. These red points are the toll collection stations, blue and green points are the GPS locations of vehicles. We compare our model with three baselines. Two of them are based on single sensing systems, and one is based on the fusion of two systems. The results shows that our model is better than the baselines of using stationary sensing system alone and the naive fusion of two systems. And also we find the performance is competitive competitive to the Oracle model based on the mobile sensing system. Finally, I would like to summarize this presentation with two takeaway messages. First, by measuring similarity across different sensing systems, we could extend the sensing ability of a single sensing system. Second, naive similarity metrics cannot capture the inherent relationship between two sensing systems, while dedicated measurements are needed. For more information, please check our paper and websites. Thanks.